Recall that a rhombus is a quadrilateral whose sides all have the same length. So here's an example of a rhombus, and you can see that all four sides really do have the same length. Take a look at these three quadrilaterals down here. Which of these is a rhombus? And to review rhombi and other kinds of quadrilaterals, click down here instead. Exactly, this quadrilateral is a rhombus because all four of its sides have the same length. So let's put a single hash mark on the four sides to show they're all congruent. Now every rhombus is also another kind of quadrilateral. Are they squares, rectangles, or parallelograms? Right, so every rhombus, including this one here, is also a parallelogram, meaning the opposite sides are parallel to each other. Now in this lesson, we'll be looking at the diagonals of a rhombus, so let's go ahead and draw in the two diagonals. Here's where the diagonals intersect, and in every parallelogram, like this rhombus here, the diagonals bisect each other. Let's label this line segment here with 2 hashes. So which other line segment is congruent to this one? And if you're not sure, click down here to review what it means to say that a parallelogram's diagonals bisect each other. Precisely, because this is a parallelogram, this line segment has the same length as this one. And similarly, the 2 halves of the other diagonal also have the same length. Now notice that the diagonals split this rhombus into 4 triangles, which will give 4 different colors. And you might also notice that each of these triangles has a side with 1 hash, a side with 2 hashes, and a side with 3 hashes. So all of these triangles have 3 matching sides. That means that all 4 of these triangles are congruent to each other according to which of these postulates? And if you'd like to review any of these, click over here instead. Great! So these 4 triangles are all congruent to each other by the side-side-side postulate. And because these triangles are congruent, that means they have matching angles as well. So among these angles, which are congruent to this one over here? Nicely done. So these 4 angles in the middle here are all congruent to each other, meaning they each have the same measure. And they also add up to a complete rotation, or 360 degrees. So what's the measure for each one of these angles? Precisely, each of these angles measures 90 degrees, so we can label them all as right angles. And so you've just proven, using the side-side-side postulate for triangles, that the diagonals of every rhombus are perpendicular, meaning they intersect to form right angles. Nicely done. Finally, try using this fact to solve a sample problem. Here's a rhombus, and let's draw in its 2 diagonals. Suppose this angle over here measures 35 degrees. Then what's the measure of this angle down here? Recall that a trapezoid is a quadrilateral with at least one pair of opposite sides that are parallel. So this is an example of a trapezoid because these 2 sides are parallel. Take a look at these 3 quadrilaterals down here. Which of these is a trapezoid? Right, this is a trapezoid because these 2 sides are parallel to each other. Sometimes you'll see sides or lines that are parallel as being marked with tiny arrows that point in the same direction, like these arrows here. Now there's another interesting feature about trapezoids we'll be covering in this lesson. Take a look at this red angle down here. Which angle in this trapezoid appears to be supplementary to the red angle? Nicely done. So this yellow angle and the red angle appear to be supplementary, meaning they add up to 180 degrees. Let's see if we can prove this is true. First, let's extend some of these sides into lines. So these 2 lines are still parallel, meaning they run in the same direction and never intersect. And this side is a transversal that crosses the parallel lines. Now this red angle seems to be about 45 degrees, but for now we'll represent its measure as the Greek letter theta. So at this point, which of these angles up here is an alternate interior angle with the red angle? Exactly. This angle over here forms a pair of alternate interior angles with the angle down here. And because alternate interior angles are always congruent to each other, that means this angle also has measure theta. So now take a look at this green angle, which is also inside our original trapezoid. This green angle is supplementary to this angle over here, which has measure theta. So in terms of theta, what's the measure of this green angle? Excellent. So whatever measure theta this angle might have, this angle up here will always have measure 180 degrees minus theta. In other words, these two angles are supplementary. And if we look on the right side of our original trapezoid, this blue angle is alternate interior angles with this angle up here, which is supplementary to the yellow angle over here. So we've proven here that trapezoids always have two pairs of supplementary angles between their parallel sides. So if you look at one of the sides in a trapezoid that's not parallel, like this side over here, the two angles on that side must be supplementary. And the same goes for the other side that isn't parallel. As a final challenge, take a look at this trapezoid here, where these two sides are parallel. Suppose this angle measures 120 degrees, while this angle measures 55 degrees. Try using what you've learned about trapezoids to determine the measures of the two remaining angles. Nicely done. If we were to extend the four sides into lines, we see that the 120-degree angle is alternate interior angles with this angle down here, making this angle 60 degrees. And the 55-degree angle is alternate interior angles with this angle over here, making this angle 125 degrees. So we have two pairs of supplementary angles inside this trapezoid, a fact which we've shown is true for every trapezoid.